So students, in this video, I'll review some R content for extreme value theory. I'm going to do this in two parts. So in this part one, I will review the sections in the theory called measures of tail weight briefly, and also the maxima and the generalized extreme value distribution. In the second video, part two, we'll discuss about threshold exceedances and the GPD, generalized Pareto distribution. That's going to be a different video. So here I have some slides. They are on ed, so under resources, somewhere you can click this link, but the link brings you to a web page. So this is hosted publicly on GitHub. So if you type this in any browser, you should get to those slides. So let's get going. Objectives of these slides. I know that the extreme value theory is quite theoretical, what we've done so far. I want to make this a little bit more concrete with some illustrations. Cover the topic of fitting data, because extreme value theory tells us that in theory, extreme values, okay, either the maximum in blocks or the exceedances over a threshold, should fit some distribution, either the GEV or the GPD. But now, in reality, if you want to do some predictions based on your data, fit a model, how do you do that? Well, it's nothing super complicated, but we'll review that in this video for the GEV, in the next video for the GPD. Okay, and also, I think I'll probably, I haven't written the assignment yet, but that's coming soon. I'll probably give you a little something about extreme value theory. So that'd be good if you can have some R tools and not have to do everything from scratch. Okay, now the first thing is a brief comment about tails of distributions. Here, I just wanted to illustrate the example we've done in class when we compare the normal to the Pareto. So as simple as that. Here I'm doing this in a function. I just want to illustrate their tails. And here I'm choosing exactly the same distribution as we saw in the lecture. So F1 will be a normal with those parameters, and F2 will be a Pareto with those parameters. And remember, those specific choices generate distributions which have the same mean and the same variance. Now, inside this function I create, so this is a function I invent. I call it compare densities. I just want to show those two densities, as simple as that. Now, the only arguments of my function will then be the range for the x values and the range for the y values. And by the way, maybe I haven't said that before, but in those videos, I think it would be good practice for you that you kind of follow along in R yourself. So maybe you want to copy paste this and make sure you can run the code and reproduce the results that are on those slides. So you learn programming mainly to practicing. So maybe it's good that you try to actively do those things yourself while I explain them. Anyway, so this function. Inside the function, what we do, we simply declare F1 to be the density of a normal. Well, we just use the inbuilt R function dnorm. F2, we need to declare it ourselves because base R doesn't have a Pareto density, but that's no problem. We create it like that. And then pretty much that's it. We're going to plot F1 using function curve. Here, there's a bunch of arguments for the visual display. I suppose you can review them, but they don't matter that much. I'm just picking a few. I'm picking different colors, and I'm labeling the axes and so on. Curve, I plot a second. Remember that if you want to plot two curves on the same plot, somewhere you need to specify add equals true. Okay, and I'm putting a legend as well. And then let's see the result. So here I'm just calling compare densities, and you see you can call a function with 0 arguments. It's just going to use the default arguments that I've specified. You see here I declare the function with those values to be used as default if the arguments are not specified. Okay, so it's plotting the two densities over this range 0 to 5 and then 0 to 1.5. Yeah. Now the point here is that we don't see much in terms of comparing the tails because we're too far away. So, and actually the normal, you know, it would go a bit further on the left, but we want to see the right tail. And here it's hard to see which one has the bigger tail. but we can zoom, okay? So that's why I declared arguments which are the range on which we want to see the function. If we zoom and we plot on a range that's further away to the right, because I want to see the right tail, I want to confirm what we had in class, which is that the Pareto has a heavier tail. Now we start to see what we want, in the sense that F2 for large values is above F1, meaning the probability to have a large value is higher for F2, which is the Pareto. And so here, recall that the distribution has a mean, but those two distributions have a mean of 1, but a standard deviation of square root of 2. So if we're at values 5, 6, 7, we start to be very far, because we're several standard deviations away from the mean, and we know that for the normal, after 3 or 4 standard deviations away from the mean, it starts to be almost impossible to get those values. But you see, for the Pareto, if we zoom a bit more, now we're really far away from the mean. You see that the normal pretty much goes to 0. Technically, it's not 0, but it's extremely close to 0. But the Pareto is non-zero. And if you keep zooming like that, you'll have that really the difference between the two curves, in relative terms, goes to infinity, right? So this highlights what we saw, that the Pareto is indeed heavier tail than the normal. And of course, maybe a comment to make is that in absolute values, those densities are both small, in a sense, right? It's even for the Pareto, it's unlikely to get a value of 8, but it's in a sense much more likely than for the normal to get a value of 8 for the Pareto. Okay, that's all I'm going to say about comparing tails. But now, maybe for the main topic, we're going to talk about the GEV distribution. And so recall, in the theory, we saw that standardized maximum, if they converge to a non-degenerate distribution, they will converge to the GEV. That's the main theorem we saw, which was called the Picklands, I think. No, sorry, the Fisher-Tippett-Gnedenko theorem said that. Okay, so here, first step, I will need to use I will need a function for the density of this GEV. So I'm declaring it here. Note that, recall that the expression, the mathematical expression for the CDF and the density is different in the case that C is non-zero or C is 0. So I declare two functions here. This one will deal with all the cases where C is non-zero, and then in the case C is 0, there's a specific name for the GEV. Under that case, it's a gumbel. Okay, so here that's why I'm declaring a gumbel, and you can double check that those expressions match. They match what we have in the slides. They're just careful. We have if else, because the support is not the whole real line. So if this condition is true, okay, if this thing is smaller or equal to 0, then the density is 0, and then otherwise this is what is going to be returned by the function, the density, in the case we are on the valid support of the GEV. Okay, again, you can check that those expressions match what we have on the slides. Okay, now what we do, I want to illustrate that the theorem works in the sense that if we generate a large sample, we take the maximum, the distribution of this maximum should correspond to what is predicted by the Fisher-Tippett-Gnedenko theorem, which is that this maximum should be approximately a GEV. So let's do a few cases. Because I want to do a few cases, I'm gonna create a function. I call it generate max. Now, careful with the arguments of this function, because there's two things. There's what I call B. That's how many replicates of my simulations I want. But there's N, and this is the size of the sample of which I grab the maximum. So careful with that. N corresponds to what we had on the slide, the size of the sample of which I take the maximum. But because I want a sample of maximums, I need to replicate this B times. Well, of course, because if I only have one sample of size N, it's going to give me one maximum. Then I don't have a distribution. So I need to replicate this B times to see the distribution of the maximum. So that's what I do here in my function. So B is the number of simulations. N is the sample size. This argument, I name it rdist, is the random generator for the distribution I want to generate. And I'm going to do that for a few different choices. Params should be a vector of two parameters for the parameters of this distribution. So, for example, if our dist is R norm, meaning I want to simulate from the normal, then those parameters would be the mean and the standard deviation of this parameter. But of course, if our dist is something else, R gamma, then those parameters would be the two parameters of the gamma. No, this is not as general as you might like. It's going to work for distributions with two parameters. Okay, A and B are my standardizing constant, because remember the theorem says that if we standardize the maximum, then we might have convergence of the maximum. And then lastly, seed, it's not too important. I just want to be able to replicate exactly the same result. So I'm going to set the seed to something. It's arbitrary. I like to set the seed to pi. You can change that if you want. And if you don't have a seed, doesn't matter. You're just going to, every time you call your function, is going to simulate slightly different results, because it's going to be based on a different sample. Okay. Now, here inside the function, what do? My max is just a vector. I declare it at first, and I'm gonna fill it with values now. The vector to contain those maximum values. B of them. Now, for, well, recall you use a for loop if you want to replicate the exact same operation a certain number of times. Here, B times. So for I repeat B times, I'm going to create a sample of observations from distribution rdist. Okay, so rdist, remember, this is going to be a random generator that I plug inside the function when I call it. So that's going to generate a sample of size n based on the parameters I've declared here. And then I'm almost done. I just need to grab the maximum from this sample. Okay, so this is what I do. My max I would be the ith time I grab a maximum from my sample. I standardize it. Okay, so I take the maximum of my sample using the function max. So max just grabs the very largest observation in the sample. Then minus b divided by a. And that's it. Note with the default values here, there's no standardization, because b is 0 and a is 1. So here you just add the maximum. Okay, and then lastly, okay, inside my function, I also plot the histogram of this of what? Of the sample from maximums, because remember, we do this b times, so at the end we have a vector of size b of those standardized maxima. Okay, and again, here there's some graphical parameters. Careful with syntax. This should be a valid random generator, yes, like R norm or one that you've created yourself. Param, a vector of two parameters, A and B are standardizing constants. I've said that already. Okay, so let's go, let's have a look. First, I try with the base distribution, so the distribution from which I simulate a random sample of size n. Let's have it be uniform, specifically uniform 0, 1. We first try with a moderately big sample size, not actually, relatively small, I mean, n equals 10. Okay, we get this shape for the distribution. Now that doesn't tell us much, because we don't really, I mean, we need to compare this to what is predicted under the theory. And in fact, for this specific case, the uniform, we've done everything in class, because we tried in class. Maybe I can switch to the lecture slides for a second, just to make sure we agree. Where was it? Somewhere we did the work, oops, to find that for a uniform with those specific normalizing constants, we indeed add convergence of the standardized maxima to a distribution that had a very simple expression, just e to the x. And e to the x, we saw that it's a special case of the what we want, the GEV distribution, okay, with mu equals -1, sigma equals 1, x equals -1. So basically, now we can add to the plot we had in R the shape of this density, the GEV with those parameters, and see if it fits. It should. Okay. And then, yeah. So let's do that. Okay, well, this is what I just explained. I actually did not need to show the slides, because I put everything here. If we standardize the maximum, specifically with those normalizing constant 1 and 1 over n, this is what we've done in the theory part. We know that asymptotically, this standardized maximum should have the GEV distribution with those parameters. Okay, so let's add the GEV theoretical on our empirical histograms. Okay, now let's just try for a very small sample size, n equals 5. You see, it doesn't fit certainly not perfectly, but it's already kind of the right shape. You see, so the red curve is the theoretical, and of course the green bars are the histogram. Doesn't fit perfectly, but it's already kind of close. And then if we try for n equals 10, fit is better. Again, not perfect, but it's already pretty good for n equals 10. And then for n equals 100, even better, right? And maybe not perfect. Maybe it's not perfect. Maybe I should have done it for n equals 500 or something, but it seems that the theorem or the theory seems to be working. Okay, so we seem to have convergence for the distribution of the maximum towards the GEV with those normalizing constants and those parameters. Okay, now let's try for a different distribution. For the exponential, again with a small sample size, here I suppose we would need to prove that the exponential the maximum of exponential properly normalized converges to the gumball, but it's the case. I think I mentioned that in class, and probably I'll give you a tutorial exercise to verify this, but I know that it's the case, and I know what the right normalizing constants are. So in this case, so this, careful, it's an exponential with just a lambda of 1. I use R gamma because my function works for 2 parameters, right? But we know that the R gamma with those parameters would be an exponential with parameter 1. Okay, and I know that the B should be log of n. Okay, you need to trust me on this, but I'll give it to you as a tutorial exercise. Okay, for n equals 5. Okay, the fit, again, it's not good, but it seems that roughly the shape seems to be correct. And if we increase n, you'll see that it seems to be converging. Okay, for n equals 10, fit seems better. N equals 100, fits gets not perfect, but it's starting to be pretty good. N equals 500, very good as well. Maybe not perfect, but it seems that we seem to have convergence. Okay, and then so I'm showing 3 cases here. For the uniform, the uniform is in the maximum domain of attraction of the reversed Weibull, meaning that the Xi is negative. Now here I'm showing a case where we have an exponential. It's in the maximum domain of attraction of the gumball, okay, which is the GV under the special case of Xi that's exactly 0. Then let's see the last case, which is a distribution which is in the maximum domain of attraction of the GV with a Xi that's positive, okay, which is also called the Fréchet. Okay, and an example would be the Pareto. So the Pareto is heavy tail, so we expect the maximum to be also heavy tail, meaning it's a Fréchet. Okay, now I think as I mentioned in a previous video, the Pareto R doesn't have a Pareto random generator, but we can easily create our own. So this is a replication of the code I presented in a previous video. I just declare our Pareto, which is going to be a random generator for the Pareto. Remember, what we're doing here is simply declaring the quantile function of the Pareto, and then if inside the quantile I plug a random uniform, this outputs an observation from the Pareto. With that done, we check again. And so again, I'm calling my function same as before. I didn't mention this, but the B, I set it to relatively high at 50,000. At first for n equals 10. Now again, with a bit of pen and paper work, you can show that the right constants that make the Pareto maximum properly standardized converge to a Fréchet are those constants, okay? But you need to believe me on this. For n equals 10, it's pretty bad, right? Like this red curve, which is the theoretical, doesn't really fit the histogram. But let's try again for n equals 100. Okay, it's still bad. While for the other cases with n equals 100, we had pretty good. Here, it's a bit better than for n equals 10, right? But it's still quite far, meaning that the fit between histogram and theoretical value. Let's try for n equals 1,000. It seems to be improving, I think. Okay, to the naked eye, the fit or the convergence seems to improve, but it's still quite far. And for n equals 3,000, okay, there it starts to be semi-decent, but you see it's still far from perfect, because on the top here, the red curve is still far from the histogram, and here the red curve is under the histogram. So my point here is just this: although it seems to be improving, so I do think we have convergence because the theory tells us we have convergence. It's much slower for the Pareto for the theorem to work. By work, I mean it seems that you require a much larger sample size for the maximum of that sample size to be roughly GEV as the theory predicts. And here we can draw an analogy with the central limit theorem. Central limit theorem tells us the average is approximately normal for a large sample size, but for different distributions, how large the sample size needs to be for the theorem to work varies a lot. Okay, for uniform observations, the central limit theorem works very well for even moderate sample sizes. But for other distributions that are very asymmetrical, you need a much larger sample size to have a good approximation. So the same can be said for the extreme value theorem. Okay, so this is to illustrate this idea that the standardized maximum converges to something that is predicted by the theory. But now another important topic is to do a bit of fitting. So what I mean by that, if you have data that should, at least in principle, conform to the extreme value theory in the sense that it's maximum data, then you want to fit a generalized extreme value distribution to it, and you want to assess if the fit is good. So this is what we do here. We import a certain data set into R and fit the GEV distribution to it. Now, this data set is some stock market returns. I'll be honest here, this is a data set I grabbed from a previous lecturer. I don't really know what it contains. I don't know. I think it's a stock index, but I'm not sure which one. So it's a bit unfortunate here. I can't really tell you what it's in this data, aside from the fact that it's stock market return. But anyway, here we just want to illustrate the procedure. So the data contains for each month in this period the lowest data yield within that month. Okay, so for every month, the lowest yield. So, but here, careful. The lowest return, we might say it's a maximum loss, even though, so it's negative, but it's the most negative it was on every single month of the in this time period. Okay, so it's already a maximum loss, so we can apply to this data our extreme value theory and see if the fit is decent. So here I'm just importing this return data into R. Using this function read table. This is the data set. I've also put it here in the R content. Okay, you can download this data set if you want to try it out. Now here, just as a detail, I don't specify any path. Okay, so I'm just assuming that the file should be in my working directory. Okay, for this line to work, the file needs to be in my R working directory. Okay, and then careful with this. Because my data here is represent the lowest values, I need to convert it to being positive if I want to have the maximum values. Meaning that here this data would be returned, so it would be like -5%, -8%, or things like that. But if I put a minus, then the minus 5% will become 5%, and then if I view this as a loss, it's going to be the maximum loss rather than being just the minimum the minimum value. Okay, I hope you see what I mean. So I'm converting the minimal yield to a maximum loss by changing the sign of those returns, because I need to have maximums. I need to have maximums to apply my extreme value theory to this data. Okay, and then let's have a look. So I take the histogram of those losses. Losses is just the name of the data set. Well, the name I gave. Okay, I get this shape. And so just by the way, just to be clear, in this data set, it contains only the maximum loss for every month. So I don't need to do any procedure to filter and grab myself the maximum loss. It's already the maximum loss. And I should have said the maximum daily loss. Okay, so let's say that in a month you have 20 or 20 something trading days. So this data represents the smallest yield, but the smallest daily yield out of every single month. So you might say that here, N, the size of the sample, is something like 20 or 22, the number of business days in any given month. We have grabbed the minimum yield, which is also a maximum loss. Okay, and this is why we might, even though n equals 20 is not very large, it might be that it's large enough such that extreme value theory applies, and this data should have roughly a GEV distribution. But let's see. That's the shape of this of those maximum losses. Now, this shape suggests, because it is asymmetric to the right, it suggests that it's not light-tailed. Okay, it wouldn't have a C that is negative. Yeah, again, because you seem to have some relatively extreme value on the right. Okay, because of that, it suggests a C that is at least 0 and maybe positive. So we try this. We try to fit to this data the GEV. Okay, and here the GEV. Yeah, okay, but actually, I think this would work. Let me just, because DGEV is what we declared before, and I think it was flexible enough that it could handle yeah, yeah, okay, this would handle a C that's negative as well, right? But let's see then if it gives us a C that's negative or positive when we do the fitting. Okay, so we do that by simple maximum likelihood. So here I'm declaring a function that's the negative of the log likelihood. Well, yes, because I'm going to minimize the negative, the log likelihood, which is like maximizing the log likelihood. You know that the log likelihood is simply the sum of the log of the density evaluated at every point. Here, in terms of syntax, the way it works, you need to declare one argument, which is a vector containing all the parameters. Here we have 3. Okay, we have mu, sigma, and xi. We give some initial parameters for the optimization. Frankly, this is not really an intelligent guess. It's just some values. I suppose we could have done a bit of work to find the method of moments estimates and feed this here would have been better, but the moments of the GEV are actually quite complicated. So I'm not sure. I don't think you can easily find the method of moments estimates. I'm not entirely sure, but I think it's a bit of work. Anyway, so then we just, again, minimize the negative of the log likelihood for certain initial values we've used here and see what we get. So, okay, so mu, sigma, xi. Mu and sigma, they don't really matter. You know, it's xi that's the main character. So xi is indeed positive. Now it's not vastly positive, but it is more than 0. Okay, so this kind of fits what we taught here, that because the data goes to the right much further than it goes to the left. Yeah, we indeed have some. We indeed have that when we do the fit, we obtain a positive xi, which corresponds to a heavy tail distribution, or at least moderately heavy tail. Okay, but now we assess the fit. So all we've done here is apply maximum likelihood to this data set. We fitted the GEV. Now we want to check if the fit is reasonable or reasonably good. If I add to the histogram of those losses the curve of the GEV with those specific parameters I've fitted. So part 1, part 2, part 3, they are those fitted estimates of the 3 parameters. And I add this curve to the histogram. You know, qualitatively, it looks pretty decent, the fit, because you don't have huge discrepancies between the histogram and the fitted distribution. Okay, but let's do a few more diagnosis. So, okay, here I'm declaring the CDF of a Fréchet. Well, Fréchet, yes, because I have a positive xi. Okay, which would be this. And I'm plotting the empirical CDF. So plot ECDF losses. We've done that before. It's simply the empirical CDF of the data. And I add to it the theoretical curve, the theoretical CDF of the Fréchet with, of course, the parameters I've fitted. And once again, same conclusion. The fit is very solid here. Of course, you have a bit of discrepancies because it's a random sample. Well, random. It's real data. So of course, you expect the ECDF to be a bit well, not smooth. Well, of course, the fitted density is smooth, but the fit is quite good. Another test we do is or diagnosis is a QQ plot. Now, so remember QQ plot, you're plotting on X and Y, the empirical here, the empirical quantiles are on the y-axis, and then to every empirical quantile you plot the corresponding fitted quantile. And remember that what you want to see, the fit is good if the data points are on the straight line, or the line x equals y. Okay, if the data is roughly on the line x equals y, you have a good fit. Now just a comment that I actually do that with the external package. So I use function QQplot. So this is a function that exists in this package env-stats. Now, if you need to install this package with command install.packages env-stats, and then you can use this function QQplot that's already implemented. I do that because I'm lazy. I didn't want to program my own QQplot function, and why not use an existing package, because it has a whole bunch of distributions already implemented. So in this argument distribution, you can plug this keyword, which the package knows is what we want here, the generalized extreme value distribution. But just a comment, it's slightly annoying. For whatever reason, in this package, the GEV is parameterized differently. What we call XC is minus XC for them, okay, in this package. I mean, you can click here. Should bring you to some documentation. So if you go and you check their expression here, it's actually when they call it, they don't call it XC, they call it, I guess this is kappa, but we had 1 minus 1 over XC, okay? So basically we just need to plug minus XC, and then we fall back to what they have. Okay, so if I go back to my code, here, yeah, you need to plug minus XC, and this corresponds to what they call kappa. So anyway, just a slight annoyance, but with that you can use their package. And here, I guess the bottom line is fit is extremely good. Like of course there's a little bit of discrepancies, but this is as good a fit, I think, as you might see in practice with real data, because the data really confirms to the straight line. Okay, and the last few points, they're known to be very variable because because they're the extreme values. So there's no problem here with this data point and this data point being away from the trend. So here I have not done a formal statistical test. So I could have, maybe I'll give it to you in the tutorial, run the Kolmogorov-Smirnov test on this sample with the null hypothesis that it comes from a GEV with those parameters. I am pretty sure you're not going to reject. Like, it seems very plausible here that the data is GEV. Okay, so bottom line here, yes, fit is very good, even though we had maximums from samples of size, a moderate size only. As I said, the number of trading days in a month, that's the sample size. Because again, we've grabbed the smallest yield in every month over this period. Okay, I believe I'm almost done. The last slide is simply a comment that in practice, maybe now that you fit a model, the fit is reasonable. Maybe you can use the model then, and you can answer certain questions. So here's just an example, but based on the model that you assume is correct, or at least you trust your model to a certain degree, can you give me the probability that next month there is a day with a minus 5% yield or worse? Maybe here I should have said there's at least one day with a bad yield, as bad as minus 5%. Well, yes, you can use your theoretical distribution that you fitted. Okay, you think the data comes from a Fréchet with those parameters that you fitted. Again, part 1, part 2, part 3 come from the maximum likelihood fit. So you can absolutely find this would find the probability that next month, or actually in any given month, the maximum yield is smaller than 0.05, because this is the CDF. And by the way, here the CDF, I declared it again, but I didn't have to because it's already declared over there. But yeah, there's a bit of replication here. But so coming back here, this piece of code gives you the probability that the maximum loss in a month is smaller or equal to 5%. So if you take 1 minus this, you're going to get the answer to this question, the probability that the maximum loss in a month exceeds 5%. And you see, it's quite modest. It's quite small. It's quite small. As a sanity check, you can go back to your histogram, and you see 5% is around here. And indeed, it's starting to be far in the tail of this distribution, which again is the distribution of the maximum loss every month. Okay, so yes, the 1% is relatively coherent with this with the data, or I mean the histogram. Okay, and again, you can answer other questions. What is the probability that next year, so next year, of course, is 12 months, there is a day with a minus 10% yield or worse? Now, think about it. How would you find the probability that there's at least a day with 10% yield or worse? Well, it's easy to find the probability of the complement. This would be the probability of the complement, meaning that in the year, there is no days with worst yield than minus 10%. Okay, meaning here this code, probability that 12 months in a row, and of course here we assume that the yields in every month are independent. Probability that 12 months in a row, the biggest loss is 10% or less. Okay, so this is the probability that 12 months in a row, you have the biggest loss less than 10%. So yes, if you take 1 minus this, you're going to get the probability that there's at least 1 month where the worst loss was more than 10%. And again, it's a relatively small number here. Okay, this is just an illustration that, yeah, once you fit your model, you can answer those sorts of theoretical questions. Obviously, there's some limits to this. Who knows if the future, the data in the future will conform to the data that you had in the past? I suppose that's always a tricky question. Okay, I'll stop here. This video is long enough. I'll make one more to talk about the GPD and the threshold exceedance method. But for now, thanks a lot for listening. As usual, I'll catch you soon.